Hi, I'm going to be making a review video for 7.3, finding the maxima and the minima. So as you can see, we have 3 objectives, 3 skills to master. One of them is to be able to visualize the maxima, minima, and saddle points on a 3D graph. The second one is to be able to use partial derivatives, which we learned before, to locate the critical point. And our third one is to be able to apply a test called the second derivative test to identify the critical point as a local maxima, minima, or saddle points for 2 variables. So let's get into it. So looking at these 3 graphs, this first one right here is a local maxima because, as we can tell from the graph, we can see it has a high point right there. So on a 3D graph, the local max is the highest point of the graph. Now, in contrast to that, this second graph over here is a local minima because, unlike this one over here, this graph has the lowest point, so it looks kind of like a bowl shape, but the minima is the lowest point on a graph, which we can see here. Now this third graph has both of them. We can see here it has the highest point from our maxima, but then this other blue line shows the lowest point from the minima. So when we can see that there's both of them, that is a saddle point. So yeah, right here we can see saddle point has both the highest and the lowest. Okay, this is our second derivative test for the local extrema. This is where partial derivatives are going to come in handy because we're going to need to find our f of xx, f of xy, and f of yy. And those are going to be our a, b, and c values, which we plug into this formula, ac minus b squared. And the information we get from the formula is going to tell us if we have a maxima, minima, or saddle points, or if the test fails. So if we plug in our values into this equation and we get a positive number, but our a, which is f of xs, is negative, then we have a maxima. If a is positive, then we have a minima. However, if we plug in values into the equation and it's less than 0, then we have a saddle point. And if it equals 0, then the test fails. So let's look at some examples. Let's look at this example. I have the equation f of xy equals 5 minus x squared plus 16x minus y squared minus 12y. So the first thing I am going to do is find f of x and f of y. So the first thing I'm going to do is find the derivatives for those. And if you look at our equation, we have both x and y values. So when finding f of x and f of y, we're just going to treat the other variable like a constant. So as we can see for f of x, my derivative is negative 2x plus 16, which I got right here. And I treat the y's kind of like a constant. And I did the same thing for y, where I treat x like a constant. Then I want to set those equal to 0 and solve for x and y, and then that gives me my critical point. So first step is to find f of x and f of y, which gives me my critical point. My second step is to find my partials, which gives me my a, b, and c values, which I can plug into this equation, which I'll write, which is ac minus b squared. So I found my f of xx, f of yy, and my f of xy, which gave me my a, b, and c values. I found my partial derivatives by looking at my f of x and my f of yy. And then I take these values and I plug it into my equation. So I got -2 for a and 0 for B, which is right there, and -2 for C, and I ended up getting a +4. So I got a positive number from the equation, and my A value here is negative, meaning I have a max. Sorry, I made a little mistake here. So I have my critical point and I have a local maxima. And to figure out what f was at my maxima, I plug in my critical point values, which was 8 and -6, into my original equation, and I got 105. So at 8, 6 on the graph, I had a maxima at 105. So my third step was to plug it into equation. And that is how we find the maxima, minima, or a saddle point from an equation and by looking at a 3D graph.